Lately, solar activity has been quite intense, resulting in more sightings of the northern lights. That's because we're at the peak of the 11-year solar cycle. While northern lights are stunning, intense solar activity can disrupt GNSS receivers and affect machines relying on GNSS, like those used in agriculture, construction, and mining. We are here with Jean-Marie Sleiwagen, GNSS expert from Septentrio, who will explain more details about ionospheric activity. Good morning, Jean-Marie. Why does solar activity affect GNSS receivers?
Well, you have to imagine those signals need to come from a satellite high in the sky. They have to go through a layer of the atmosphere, which is called the ionosphere. And the ionosphere and the propagation within the ionosphere is very much affected by the sun and its radiations. Typically, the ionosphere is a quiet medium. It only affects the delay of the GNSS signals, and receivers know how to deal with that. This is not a problem. Problems occur during high solar activity or things like solar flares, where the sun is emitting a lot of radiation at the same time. When this hits the ionosphere becomes unstable to the point that GNSS signals are affected and sometimes even unavailable. And we call that scintillation. And now you have to know that scintillations are not affecting all of us in the same way. It's mostly affecting the equatorial regions and to a lesser extent the polar regions.
So, what can be done to protect the receivers from this solar activity?
Well, luckily, compared to the last solar cycle, we have much more satellites and signals available. And what we see is that most of the time, a subset of satellites remain usable, unaffected by scintillations. So the key is to identify those satellites that are still usable and exclude the others to avoid that they drive the position away. And that's exactly what we do in our IONOPlus technology, this classification between bad and good satellites. Next to that, we have the LogPlus technology, which has been developed to keep on tracking signals during vibrations or shocks or all types of instabilities. And we see that it greatly helps as well during scintillations. So those two technologies, IONOPlus and LogPlus, work together against ionosphere scintillations.
What about a base station? Would that help as well?
Well, base stations which are needed to provide you with corrections. Typically, you may have a single base station or a multiple set of base stations in a network. A single base station is typically located nearby, and I would say it doesn't help a lot. Why? Because this single base station will be affected by the same scintillation as the one that is affecting you.
Right.
Networks, on the other hand, they combine receivers and make corrections from a lot of receivers. And those corrections typically are less affected by scintillations. What those networks cannot do is to predict exactly when and how a scintillation will affect your receiver. This is because it's a very local phenomenon. It's like predicting lightnings. You can say it's a thunderstorm, there is a danger, but you can never tell exactly when lightning will strike at your place. So the network can help, but only partially.
Right. So Septentrio has developed these technologies, IONOPlus, LogPlus. What is Septentrio's experience with solar activity?
Well, back in 2014, during the last peak of the solar activity, we had a network of receivers in Brazil collecting a lot of data during scintillation. And from this data, we learned how GNSS is affected by scintillations and how to improve our receivers. The main outcome at that time has been the development of the Polarix 5S receiver, which is now, I think, the reference in the scientific community to monitor the ionosphere and used by many universities worldwide. But the good news is that the same technology is now included in all our receivers to the smallest module.
Thank you very much for your time.
You're welcome.